CLion a cross-platform IDE for C and C++. Download now.
Wow. Well, what a great conference, eh? Yeah? Once again, I want to say thank you to Guy and everyone who's made this possible, because I've had an amazing time this week. It's been really, really great. I've learned a bunch of things, and as the person who gets to go last, that means I have to change my slides in light of what I've learned while I've been here, which will throw off all my timing. So when it takes, more than the 2 hours I've been given, then, all right, I'm just trying to josh with Guy here. So this is a better form, right? Everyone can see this? So I don't know how many of you, who all knows what the heck a ZX spectrum is by hands? That's a lot of you. That's impressive. And so did you spot like the lanyard, and the spectrum is a really appropriate thing in so many ways. Obviously it means something to me. It can mean a lot of things to other people as well. And it kind of encompasses all of those meanings, I think. But for me, the spectrum logo is all about my childhood and my introduction to computing and kind of the beginning of my journey to where I am right here. So I'm the old dog in this. This is me. I'm in between jobs at the moment. I've finished my previous job, and for contractual reasons, I can't start my new job until the end of this year, which is boo-hoo, poor me. I'll be starting with HRT, one of the sponsors of this conference. So, thank you, HRT, thank you. I don't work for them yet, contractually not allowed to, all that good stuff. Anyway, so why? I wanted to do something cool for this keynote, and it occurred to me that I'm kind of getting a bit older in my career now, and I've been giving out wisdom to other folks that may be in need of updating. In particular, I'm quite cantankerous about build times and compile things like templates and constexpr and all. I know there's lots of people looking at me with tutting eyes right now. I'm sort of an old school, I'm an assembly programmer at heart, and I've sort of clawed my way up slowly, and it's kind of hard to let go of the old ways. So I thought I'd try and teach myself some new C++, like the newest I could find, and I'd do it through the medium of writing a program that I know well and I would enjoy writing. And I'm going to do it twice. Once the old way, the way that I would write it naturally, and then the second time with all the modern things, and then I could compare and contrast and see what came out of it. So you all know me from the website, right? That is Miracle, the Sega Master System emulator. No, of course, I'm joking. No one really knows that website. It's JSB, the BBC Micro emulator. Yeah, no, so this is my hobby. I love doing these things. Emulators are a great way of learning about how hardware really works, and also just having a fun program at the end of it all that has some nice output that you can play with, right? Spectrum was my first computer. I got it on my 8th birthday in 1984. One of my dad's colleagues' sons had written a happy birthday program in Spectrum Basic and gave me a cassette alongside the computer, which I loaded up, and I had, happy birthday, Matthew, and it was like a little swimming person. I was into swimming at the time, and I was blown away by that. And I'm actually getting quite emotional now, because this is actually like how I started. This is what really put me on this journey to be standing in front of you all, right? And so I hit break, looked at the program, and started learning how to program. But obviously, mostly we were just playing games, right? Okay, there's going to be a lot of game shots in this. What game's this? Manic Miner, exactly, right. So let me just quickly go over what my old dog, cantankerous old man view of C++ is, contemporary C++. I think we're beyond postmodern C++ now, as Tony Vernier several years ago said. This is what I don't like about all of the things in C++ right now. Long build times. Yeah? No? No one, never, you're fine. Everyone's happy with build times. It's just me. Okay. Terrible error messages, right? Yeah. Modules. I've been told that they don't work. Anyone using modules in anger? Let the record show no one, maybe one half hand went up. Coroutines are complicated. Now, again, most of these slides were written before I attended this conference, and there's a lot of useful talks that I've been to now that have changed my mind about some of these, so you're going to see that. So I'm going to challenge myself to write and use all the things I say I don't like, which is constexpr and consteval. I'm pointing at Jason Turner in the front row. I've just come out of a talk of his where he goes into when to use consteval. Template metaprogramming trickery. I've always hated it. It feels like I'm programming in the wrong language. I'm not really a functional programming type of a person. Concepts, modules, coroutines, all these things that sound complicated to my poor assembler programmer brain. So I chose this spectrum because it was really important to me. It's part of my childhood, as I say, and because I thought it's a pretty straightforward machine. There's hardly anything in it. And so I, chose to write this twice because, not because it's easy, but because I thought it was going to be easy. And because a friend nerd-sniped me into it. Because once I discovered it was difficult, I mentioned it in passing to somebody, and that person was like, yeah, but I had that one growing up as well. I'd like to see that too. And so I was like, all right, I guess I will. And then she said, I'll help you if you do it. And that was Hanna Dusakova, for whom the only way I've got any of the cool C++ things that you're going to see today, if you think they're cool, the only reason that they're working is because I had a lot of help from someone much smarter than me, and that person was Hanna. So let's talk about what a Spectrum 48K is. It has a Z80 chip in it. This is a Z80 chip. There's a photograph of it up there. This is actually, the Z80 was in my Spectrum Plus 3, which I got a bit later on, and it's the only part of the computer that remains. Everything was socketed back in those days. So we've got an 8-bit CPU running at a blistering 3.5 megahertz. I know, the crowd goes wild. 48K of RAM, and 16K of ROM, and then this custom ULA, which is posh for like a sort of custom chip. It's not that custom, it's just a pile of logic gates, but then, I guess, strictly speaking, all chips are just a pile of logic gates, really, but, it's a bit more straightforward than that. And that custom ULA did everything else in the entire computer. It generated the sound, it generated the picture, it dealt with the loading and saving from mass storage, which in the case of a Spectrum was an audio cassette where horrible screeching noises were recorded onto it and then played back to load up the games. Inside that Z80, we've got a bunch of registers. So this is a quick overview just so that we can explain what's going on. We've got 8-bit registers. The A register is kind of the main register. It's the accumulator. The B, the C, the D, the E, the H, the L, and the F. Obviously, the exception proves the rule of like having something straightforward. The F register is the flags register. It sort of holds extra special information about whatever happened with the last arithmetic thing that you did. If you subtracted two numbers together and the result was negative, then the flags has a negative bit set in it, things like that. One of the cool tricks the Z80 did is it let you pair up registers in a particular way. So B, C, D, E, and HL. Those are like the B register and the C register sort of stuck together. And you could treat them as 16-bit values. So you could do some limited 16-bit arithmetic. And this is the only way you got pointers. So HL could be used as a pointer to point into memory. And then you could kind of read and write. So, that gives us 16-bit pointers. We were talking about this in the previous session. So we have 64K's worth of address space to deal with, a massive amount. Interestingly, although it could do some 16-bit arithmetic and obviously 8-bit arithmetic, inside it was actually only 4-bit. And it was a cheaper part that they just did twice. So every single arithmetic operation would take 2 clock cycles to do 2 4-bit adds and then kind of deal with the result. Anyway, that's off topic. It has some strange shadow registers, which you could sort of switch in and out from. There were some genuinely 16-bit registers, the IX, the IY, stack pointer, and the program counter, and then some special registers we don't need to talk about. So let's look at a Z80 program. It doesn't really matter what this is doing. What I really want you to realize is that computers just look at numbers in memory. That's all they do, right? There's very complicated ways of staring at numbers in boxes in memory, deciding what to do with them, and then moving on to the next number. So this program, the left-hand side is the bytes in memory, the machine code. That's what the machine sees. On the right-hand side, the sort of ASCII text is the human-readable version of it, and I use that advisedly, human-readable. And we use, colloquially, we just talk about assembly and assembler code all the time. And we don't really make the distinction between the machine code and the assembly code, which is the sort of like source and binary format of it. But anyway, so the machine is going to read 3EFF. And what that means is load the value FF into the A register. So far, so good. The machine reads 013412. And the 01 means this is a 16-bit load of the BC register. And so 3412 is, of course, 1, 2, 3, 4, the other way round because nothing's straightforward. This is little endian, right? Which is the correct endian? Anyone going to take me up on this? There's little endian and wrong endian, right? Okay. A single byte instruction here, just O2 means load BC with A, and that brackets means sort of treat it relatively. So that's where I'm treating BC as if it's a 16-bit pointer, and I'm storing the A register into it. So the left-hand side is sort of the destination, the right-hand side is the source. Increment BC, decrement A, and then JRNZ means like NZ, gosh, been in America too long, NZ, means jump relative if not 0. So that's referring to the last sort of arithmetic operation that happened. In this instance, that would be the decrement. So we're saying we decrement the A register, and if it's not 0, go back to the top of the loop. And so that 2O means JRNZ, Z, and the FB is like back 8 bytes worth. So that's our loop, and then we return. So now you all know how to read Z80 assembly, and you understand all of the bits and pieces going on here. Obviously, you'll be putting the compiler explorer into Z80 mode next time you're using it, I'm sure. Before we move on, the memory map. So you're probably used to virtual memory, right? You can page memory in and out. No such luxury on the Z80, well, on the Spectrum specifically. The bottom 16K was just the ROM. Right? You read from it, you get ROM, you write to it, nothing happens because it's read-only. No faults, no traps, no nothing. It just didn't do anything. Anything above that was reading and writing to the RAM, with a little sort of exception that the addresses between 4000 and 5800 in hex actually refer to a piece of memory that the video circuitry, and by that I mean that ULA chip, that's also reading that memory, and it uses it to produce a TV picture. So if we read and write to that, we're seeing what's being displayed on the screen. Fabulous. So we can write an emulator now, right? Here we go. We're going to have some chunk of 64K that I'm going to say this is the whole memory of the computer, the whole address space. I'm going to take 16K of it, and I'm going to memcopy some ROM that I've got from somewhere. You know, if I kept the ROM chip, I could have dumped it, but I found it on the internet. And I could probably have used hash embed to get it into the source code, right? That would have been a cool news if I only thought of recently. I'm going to have a function to write to memory, and all I'm going to do is I'm going to make sure that you're not trying to write to ROM. Otherwise, so I just discard it if you're trying to write below 4000. I'm going to have some storage for all my registers, and I'm going to treat the registers as all 16-bit, and then if I'm reading the A register, I'll sort of shift it down or I'll mask out the bits that I need. In C, you could use nice unions for this, right? And my assembly programmer brain wants to use that, but I can't do that in C++ without, there's lots of shaking heads about undefined behavior related things, so we can't do that. All right, let's write the emulator then. How hard can this be? Right, so we're going to say forever, switch on the first byte where the program counter is, right? We're going to read the memory at the program counter, and we're going to see what number it is, and that number will tell us what operation we need to do. If it's 0, that just happens to be NOP. That's the easiest one. Fantastic. We just do nothing, and we carry on, and we'll read the next byte the next time round. If it's 1, if you remember, that was that load BC with the 3412, right? So the next two values in memory, PC++ and PC++ again, we're going to put those into the BC register. Number 2 is that indirect writes through BC. So we're going to treat BC like a pointer, pass it to the write function, and get the A register out. Increment BC, BC++. Hey, this is easy. How many more of these can there be? Yeah. Well, I mean, I just sit down. Well, this is the table of all of the opcodes. There's 256 of them, but you notice 4 of them are a different color. Those different color ones are like, actually, this is the first byte of a multi-byte opcode. There are more. So in total, there's about 700 instructions. Now, most of them are very, very similar, but still 700, that's a lot. And we don't have illegal instructions on the Z80. You know, like nowadays, if you just executed any old random bit of memory, soon enough you'd find a byte that wasn't a valid instruction on whatever CPU we're on, and it would throw an exception at the hardware level. You get SIG-ILL on Linux or whatever, or a crash in Windows. I don't know what Windows does, actually. No such luxury here. Any sequence of bytes we feed into the CPU has some kind of side effect. And games programmers, and I'm looking at games programmers here, they will find useful sequences of bytes that do something convenient and useful, and they will use them in their games. So we have to emulate everything, and it turns out about 1,400 of them are actually valuable and useful. And so if we want to emulate games, 1,400 instructions. Gosh, that's going to take a while, right? So we've got an awful lot to do. Okay, which game? Jet Set Willy, correct. This is Maria, the housekeeper, telling us off for leaving the house in a state. All right, what about this one then, Guy? So I'm going to talk about the first implementation while this is actually from the Horizons tape that came with the computer. You press play on it, and it drew a picture of all of the parts. So I could have just showed you this, I guess. Okay, so I've done this before a bunch. And the way that I typically write emulators when I'm emulating a CPU is I will grab the list of all of the instructions as like a text file, or if you're really lucky, HTML or XML or whatever's actually built this web page that I stole this screenshot from, and I will parse that out, and then I will generate the code. Because if I've got a 4,000 line file that has LD, that says, first of all, it says NOP, then it says LDA, BC, like literally the strings, right? That's what you can use to write a disassembler, and then I can write some naff bit of Python to split it and then work out what's happening, and then I can just emit C++ code, and then I can generate each case statement automatically. And that's typically how I do it. And in fact, in those emulators you saw with the BBC Micro and the Master System, one of them uses a Perl script to generate all of the opcodes. The other one, because it's written in pure JavaScript, actually the creator, the thing that looks and generates all the instructions table, is written in JavaScript inside of itself. And it kind of does this sort of like sort of snake eating its own tail thing where it creates text and then it evals it to turn it into a function and then starts running it. So it's kind of just in timing itself. It's fun. But I didn't want to do it that way this time because it feels cheating. It feels like I'm not doing it right. So I'm going to do it another way, which is I'm going to try to decode it in code, like that switch statement, but I'm going to try and do it a little bit more principled, right? And the principle that I would like to do is something like this. I'm going to have some kind of abstract notion of what an instruction is. It has some string name, an opcode. It has how many bytes long this particular instruction is, so I can move the program counter on. It has some abstract source and destination, where the source could be which register it is, or it might be, hey, no, this is a value I need to get from memory, or it might be a constant, right? And the reason it might be a constant is because there are increment and decrement instructions, and there is add instructions. How much more convenient would it be if I decoded an increment as just an add with the constant 1? Hey, I have reduced the amount of code I need to write. Fabulous. So those operands can be 8-bit registers, 16-bit registers, the destination similarly, and then the op is the operation, the actual thing we're going to do. And by doing this, what we're hopefully doing is taking that 1,400 space of all these possible instructions and boiling it down to maybe a dozen types of operand, and then maybe a dozen operations. And as long as we can decode those bytes into that, I don't have to keep writing all these different permutations and combinations. So the code might look like this. We do some kind of decode, whatever the heck the program counter's pointing at, go get the operands that it says that we need, execute them, and then write back the result. Sort of looking a bit like if you've ever studied hardware design, the standard way that CPUs work, which is cool because we're emulating the CPU. And then, this is maybe what our decode routine could look like. I can now group together very common operations, like 4, 14, 24, and 34. Pattern forming. Maybe there's a pattern in this. These are all increments. And so I'm going to say it's an increment, and it's an 8-bit add, and it's adding, I decode whatever the destination is, and then the operand is 1. Okay, this is cool. So far, so good. I have to emulate the arithmetic unit. The ALU is the arithmetic and logic unit, and that's going to do all of the actual calculations. And these are all the operations it's going to do. We've got 16-bit adds and 8-bit adds, and they're as straightforward as this, right? So it doesn't take too long to get something up and running. But it's, of course, never that simple, right? Because two things. One, I need to update the flags, right? These additions might cause something to become negative, or it might cause something to overflow, or it might cause something to have a carry. And also, as I discovered rather late into this project, inside the chip, incrementing isn't actually the same as adding 1, because you can do increments a lot cheaper in hardware if you know it's by a sync, like literally the value 1. It's got a clever little ripple thing, and that doesn't update all the flags in the same way. So I had to sort of scratch that, which was a pain. So this is what the flags look like. We don't really need to worry about them. They're just essentially a bit mask of interesting things that happened in the last instruction. And this is the awkward code for adding two 8-bit numbers together, right? So something which is one operation on the Z80 is 15 lines of pretty complicated and gnarly code. The irony is, deep, deep, deep inside the x86, right, which is derived from the 8080, ultimately, that is the sibling to the Z80. because the person who designed the 8080 left Intel and went to form Zilog and actually made the Z80 sort of in the image of it. So deep inside the x86, these flags also exist, and if I could get access to them, I might have been able to use them. But I wanted to write this in like straight, nice C++ and not use horrible assembly intrinsics and things, because that would kind of defeat the purpose of this. Anyway, putting it all together, it looks like a CPU. We fetch, we decode, we execute, and we write back. Brilliant. Okay, done. So I get to the point where I have the 16K ROM of the Spectrum loaded into memory, and I write the world's worst GDB equivalent here, which is, it's okay. I can single step through and I can disassemble stuff. And I can, run a few instructions. I can even set breakpoints if I had to, because, debugging this is a nightmare, incidentally, right? There's one thing when you're trying to debug a program who you have the source code to. There's another thing where you're debugging a program for which you do not have the source code to, and you can't trust that adding two numbers together actually works. So this is the world you live in. But I had the annotated disassembly of the Spectrum ROM, because there is a community of folks who do this kind of stuff, and we reverse engineer and read back over old source and old assembly and work out where everything is. And I could sort of step through, and I could develop some confidence that it looked like it was booting up. It was clearing all the memory. It was starting to write to the screen. Oh, maybe this is cool. So it would be nice to see what's going on, right? So let's talk a little bit about video output. That area of memory between 4000 and 5800 is interpreted by the ULA as this sort of 1 bit per pixel display. So it's a black and white display, except each 8x8 tile can have a different foreground and background color. So there's kind of two parts. It's quite clever. There's some really neat tricks it does internally because the hardware is so embarrassingly simple. But by and large, it's pretty straightforward. I don't really have time to go into it now, but that is the way that the screen is. So you write some code that interprets the memory in that array and turns it into RGB values, and then you get on with your life, right? Then you write like an SDL app. That's all the rage I heard. I don't think it is. I just asked ChatGPT to make it for me, and it did. And I kind of then fixed a few bits and pieces. And so basically the loop is every 50th of a second, emulate a 50th of a second's worth of CPU instructions, and then take the bit of the memory inside the chip that corresponds to the video, turn it into RGB, and put it on the screen. And we get to demo time, which is, you've been very patient so far. And now we get to test your patience further by me seeing if I can actually do this. Oh, look, it came the right way. Yay. Okay, there we are. There is a Spectrum. Oh, no, hold your applause, you lot. No, go on, you're very easily pleased. So, who among us has not been into a department store in the 80s where, okay, lots of hands are going up here because there's a definite divide in the crowd. Or Dixon's, right, for the Sun, and broken into whatever demonstration program they had for their computer and done something like this. Yeah, or local equivalent, right? There we go, yay. Yay, thank you. I pressed the right keys as well, there we go. So those of you who might have looked at the Spectrum that our wonderful photographer brought in, thank you, photographer person, wherever you are, or the Spectrum Next that someone else had brought in as well, you'll notice the keyboard is very odd. And I'm wearing the t-shirt that has, unlike some of you who are wearing the conference t-shirt, which has some of the keys, this one has all of the keys. And so you have to know which key has what, because in order to make your life easier, all of the keywords of the basic language were on each of the keys. And so to type print, you press P, great. To type go to, you press G, that's easy to remember. To type load, you press J. Of course, everybody knows that. It's muscle memory for a whole bunch of people in here. So you have to remember them, and there's symbol shift and all sorts of things. Okay, well, that's boring and everything. Let me just get my mouse pointer onto the Linux terminal on the other screen. Let's do this again, this time with, oh gosh, over here. Sorry, it's too many, and we won't put it in training. Now, I don't know, this won't come out on the recording, but some of you are being tortured in the ears by the noises my computer is making on stage, which are just absolutely ghastly. But that was it, right? I'm going to turn that off now, mute it. Oh, gosh. So this was like one of the first and still probably best platformers And I'm going to demonstrate how excellent I am at it by, oh, am I going to make it? Yay! And I've got the lag of looking at the secondary screen here as well, which is how I'm going to excuse how bad I am at this game. But like this passed for high-end entertainment in 1982 or 1983. So, and you're going to die. Okay, right, well, there you go. Anyway, so the thing about emulators, if I can find the control key, there we are. The thing about emulators is that they have like a hockey stick-like reward function, right? You got nothing, 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 runs for a bit and then hits an instruction you haven't emulated yet. All right, nothing, 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 okay. And then games start working and everything works. And you're like, whoa. And then of course you lose weeks of playing old games and getting back into it. You know, that's how it goes. And you know, you get some amusing bugs along the way. Yeah, turns out the bits weren't the way around I thought they were. Yeah, anyone, the spacefaring game Elite, originally from the BBC, yeah, BBC B, but then ported to the Spectrum, and this one was particularly insidious. This was just like some weird index register thing I'd gotten wrong, and that was not straightforward. It's a miracle that it booted and ran to this point and had this error instead of just getting stuck in an infinite loop somewhere. I wrote some tests because that's what you're meant to do, and in fact, it was incredibly useful. Oh my gosh, right. So the catch-2 tests I wrote for this had simple tests of the ALU, like adding two numbers to the gives me the right answer and the right flags. Of course, trying to work out what the right flags were is difficult because they're not necessarily that well defined. And then luckily, because there are lots of crazy people on the internet, somebody's written like a test suite in Z80 assembly that is a test for the Z80, and it kind of runs every instruction possible, and then it kind of hashes together all of the registers together and then compares it against the known good value. And it's been run on a real Z80, and so if you get the right value, it's a perfect emulation of a Z80. Congratulations. If it doesn't, you've got no idea which one of those instructions is wrong. I passed that now. So this is my first approach. I should have said that before. This is obviously just me getting it to work and reminding myself how this all fits together. Overall, about 1,000 lines of code split between the decoder and the executor. There's some shareable code. That is code that I'm not going to try and re-implement in the second part because, frankly, it's just too miserable to get right. The ALU, the flags, the registers, that kind of stuff. Build times are the thing that I care about because I'm a TDD person and I'm also of short attention span. So what I really like to be able to do is to add a test, hit the button, and get some reward almost immediately, right? If it takes more than a few seconds, then I'm starting to reread it again, and then I'm like, yeah, whoops, that's been sat there with an error, compile error for the last 20 minutes, and I haven't done anything about it. So what I do is I edit the implementation such as I would be if I was testing a change, and I run, and I get to the tests, and I did it 3 times back to back. Each time I'm making that same change. This is no caching or anything like that. And it takes 2 seconds, 3 seconds. That's my happy place. I'm really pleased if I can just press buttons and I'm seeing the fruits of my labor. This is the code generation. This is the x86 assembly of the decoder for the Z80. I know it's confusing, right? The only thing you should note about this is that that's massive, right? And again, I tell people when I do any kind of training, you should never judge how fast a piece of code is by how many instructions it's running, but this is terrible. And it's calling other functions, so blah. Anyway, that said, modern computers, even this naff old laptop, are super fast. We emulate, even with that nonsense code, a 300 megahertz spectrum, which is so cool. That's 100 times faster than the original. So that's my first one. I was underwhelmed with my achievements, I'll be honest with you. It was fun, of course it was, right? I got to play my old games. I was hoping for a much faster piece of code out of it all, and ultimately it was a bit unrewarding, but I was like, no, this is cool, that's great. I'm gonna take that, and I'm gonna move on to the second version, which is gonna be all the cool C++ things. And I had a secret plan that the way that I'd written the first version would segue naturally into the second version, and I could you'll see how well it worked out as well. So, second implementation. I'm not gonna ask what this one is. So what did I learn from the first version? Well, I didn't really show it, but that decoder, the one that had all the switch statements, that was still pretty ugly, right? There were still lots of cases in there, and although I could group a lot of them together, and in fact, at one point I was using a GNU extension where you can do case value dot next value, and it does it cases all of them together, between 0 and 8. Not standard C++, which kind of defeats the point. Didn't help that much. And obviously, I hated the code generation. That's kind of my thing. So this is where I was going from the beginning. This is what I was hoping for. My dream implementation is to have a relatively straightforward, understandable decoder that I can run at any instruction. Then I can build a sort of constexpr function that does exactly what that opcode decoded to do. So if it says it's an add and it takes this register and that register, then I can build the bespoke function using constexpr trickery that does exactly that function, and then make a table of 256 functions, and then just call that function. So I just literally read the next byte of memory and jump to the function that does exactly the right thing for that instruction. Fantastic. And all of this at compile time because, you know, constexpr, something. So, you know, ultimately, that whole loop that I had before with the decode and all that nonsense will be this. Read a byte, dispatch to it. Wonderful. OK, we're going to move over to not valid C++, and I will make no apology for reinventing CSS flashing here. It took me a while to get that working, actually. This is how the flash would work on the Spectrum. There was like a hardware flashing system. So what I really want to do is I want to make an array of 256 pointers to functions, which is the result of taking the values 0 through 255 inclusive, decoding them as if they were an instruction and breaking them down into what I need to do, somehow magically compiling them into a function using, I don't know, something constexpr something lambda, and then turning it all into an array, right? You can see where I'm going with this, perhaps, and some of you are smart enough to know where I am going to be going. So again, this is not valid C++ because there are some, the astute among you will notice things that you can't do in C++. So this is what the compile function I would like to be able to write, right? It's a const_eval function because that means it can only happen at compile time, right? So I should be able to do all these things perfectly at compile time, right? It takes a decoded instruction, but it also has the word constexpr up there. You can't do this, it turns out, because what I really want to do is to do all of this work at compile time. So given a particular instruction, I want to work out how to read the value for that particular operand, both of the operands. I want to work out how to write the value for that operand, and then I want to work out what the executor is, what's the actual operation I need to do for it. And that can be decoded statically at compile time. And then at runtime, this bit runs and just runs those three things. And the compiler should see through all that and just do the perfect thing for that particular decoded instruction. And then we set it back. And so this is what, you know, my again, none of these things are valid C++. You know, my const_eval getter for, I give it an operand, and I do a switch constexpr, which was hilarious when Daisy actually showed this yesterday in her keynote. I was like, hey, I was looking for that yesterday, or like in my presentation. And so, you know, for each operand, I want to say, like, well, this is how to access the thing that has been decoded for that. And this should just be straightforward, right? But again, you can't do that. Switch operand isn't, switch constexpr isn't a thing. Returning a little lambda that gets that thing. I can't do this because I can't have a constexpr parameter. And I tried some other tricks. I tried getting, you know, trying to use templates at this point. And, you know, here I'm saying, well, if I can't construct something, maybe I can make a template. I was trying to avoid templates, right? This basically what this boils down to is I hate programming using templates. Templates are brilliant for generic code, right? If you want a vector of t, and t is an int, fabulous, go knock yourself out. But if I have to encode the Fibonacci sequence by recursively instantiating templates or whatever, count me out. And so I see constexpr as like a way of doing a lot of the things that I'd otherwise have to use templates for, and I was hoping to use it for this. But you can't do this. I can't even use templates at this point here because, and as Jason's in last talk we were in, you know, as much as we want it to be true, we can't take anything that's a parameter to a function and build anything that's constexpr out of it, and we can't use it to instantiate templates or anything like that. So I can't make the values 0 to 255 in this way and call a normal function with them and just do what I was doing, right? It just doesn't work, right? And this is the first point of learning for me in my journey. First point of discovery in my becoming a better programmer was constexpr doesn't work like that. So the parameters to constexpr functions are not constant expressions. Even when you make them const_eval, you want them to be. In fact, Jason was just telling us this in the last meeting, the last session. And so although the compiler absolutely does know the value of all of these things, you can't take advantage of that in the way that you want to, that I want to. You can't instantiate templates from parameters that were passed to constant eval functions. And you can't do any of the other tricks that I was trying to do. So I was very frustrated and annoyed. And I was even more annoyed, incidentally, that Thorin did not sit down and start singing about gold in this screenshot. I spent ages, right? Anyone who's played this game, what is it? The Hobbit. Yes, it's pretty obvious, isn't it? So at this point, I was about to sort of give up and try a completely different tack. So we're going to have a brief interlude. And I went on a journey of discovery because I thought to myself, I've got like 3,000 lines of code, and I'm currently emulating a chip that has 8,500 transistors in it. That's almost like one line of code per 3 transistors. That doesn't seem like the right ratio, right? Surely modern programming techniques should mean that I could do this in a more succinct way. So somehow this chip is doing something that I need to do much more simply than I'm doing it. So this is what a Z80 looks like if you take the top of it off and you take a bunch of high-resolution photographs. It's about the size of your fingernail. So hiding in this big plastic package, really, is a tiny little thing in the middle of it, and all of the wires are just there because it has to be able to plug onto a circuit board. It looks like this. And if you zoom into that bit at the top, this here is called a PLA. It's a programmable logic array. It is effectively sort of like a ROM-ish on a chip. And I was going to say sort of like a ROM because it's not just ones and zeros and strictly looking up in a table. There is effectively ands and ors and nots in here, and they're arranged in a regular pattern, and then the shape of the thing over the top of it says, well, if this bit is set, and this bit is not set, and this bit is set, and this bit is not set, or whatever you pick, then I am active. Now, obviously, this is a picture. Thankfully, there are very lovely people on the internet who have done all the work for me. This is Ken Shirriff, whose blog is fantastic. If you love this stuff, go look him up. This is rotated 90 degrees from the picture you saw before. What we've got coming in at the top are all of the bits of the opcode, the value that I said that's 0, that's NOP, and 1 is load with BC. And then these are the different rows that get energized when these particular patterns of bits come in. And then the energized row goes off to turn on, I don't know, the loading and storing unit, or it turns on the adder, or it turns on the thing that turns the adder into the subtractor. All of these things, all of these bits of what are hidden in the opcode are actually just relatively straightforward bit manipulation. Okay, maybe we can use this. So even simpler than that, someone even cleverer than Ken has said, okay, there's a pattern hiding even in that 100-odd line table. And so what we can do is we can take the opcode coming in, that 8-bit value, treat it as X, Y, and Z, where X is the top 2 bits, Y is the middle 3 bits, and then Z is the bottom 3 bits. And then we can build a relatively simple table that's kind of like the unified theory of decoding, right? There's not as many cases. And so what we'll do is, if X is 0 and Z is 0, then there are 8 possibilities for Y. 0 means not, 1 means exchange, 2 means decrement and jump, 3 means jump, 4 means jump conditionally, and now 4 through 7, means jump conditionally, and now we can just look up in the table what the 4 different cases of that jump is. Okay, that's slightly simpler, but not much of a win. So far, it's a bit like a switch statement. Okay, how about if X is 0 and Z is 1, now we look at the Q and P bits, which is sub-bits of the Y, and there are 2 cases. We're either loading a 16-bit value, or we're adding a 16-bit value to HL. Okay, all right, this is simpler. Increments and decrements are also quite simple. This is the best one. If X is 2, now bear in mind we've only got 2 bits, so there are 4 possibilities for X. So having one case for all, for one value of X is a quarter of all opcodes decode as an ALU operation, which we can look up in a table based on Y. So it's add, subtract, exclusive OR, and all that good stuff. And then the register that we pick from Z. Okay, so there's a pattern in here that I didn't spot when I was just doing my case statement. So I kind of could see that there was something going on, but I thought it would be far too complicated for me to work out, and I'm glad someone else did. So I've got a new approach. Okay, good, right, we've been on our interlude. I'm going to go back to my C++ code, right, because I'm losing some people here. So we've got to get some C++ code on the screen. So my new approach, I'm going to make a class. I'm going to accept my fate. I'm going to accept that templates are going to be part of my life. I'm going to make a class for each category of instruction. So 16-bit loads, one type of class. ALU operations, another type of class. NOP is a type of class, all that good stuff. For the ones that have different behavior depending on some of the degrees of freedom, the ones that have a parameterized on which register they're acting on, or parameterized on whether they have the carry or they don't take the carry, things like that, the things that came out of the table, we're going to templatize that class on them. So I can specialize the class for its particular operands. And then, a bit vague now, somehow I'm going to use the X, Y, and Z bits to select which of these classes is the right class to do the work for this instruction. And then somehow we're going to build a compile time table, just as we wanted at the beginning, to dispatch to the right class. All right. This is the trick that we came up with. And by we, I mean Hannah came up with it and told me I was stupid for not thinking of it myself. But that's Hannah, bless her. So this is what a NOP looks like. We've got two sort of fields, and it's two static fields. Really, these are just sort of like namespace kind of objects-ish, but we need to be able to address them. We've got a mnemonic class. Mnemonic is just a string, but you can't have constexpr strings because of reasons. So this is just a fixed size buffer that's the biggest mnemonic that any opcode has, and we just sort of copy the bytes in. And then we have an execute function. Obviously, NOP is, again, the easiest instruction to implement, so we do nothing. Fantastic. What about a 16-bit load? So this one is a 16-bit load into one of the 4 possible 16-bit registers. And so we need to get the mnemonic, and the mnemonic can, in fact, use std string. So the LDS there is a std string of a load. We're going to add in the name of whatever the P register is, and then we're going to add in this comma NNNN, which is just the placeholder for the number we're going to be reading in. And then the result of that is a std string, which luckily we can copy into our mnemonic, and then the std string dies before the end of the compilation, so we're good on that front. We haven't let a std string live beyond the compile time. So far, so good. Okay, I can do some limited amount of string processing at compile time. Who knew? And then the execution, well, again, we can look up these things in a table. And this is all constexpr. P is a compile time constant. These two tables are constexpr tables of things. And we're just going to read the 2 bytes that correspond to the 16-bit value and poke them into the relevant halves of the 16-bit register. And critically, all of these are known at compile time, so the compiler will generate the exact right code. There's no further indirection inside the compiler, whereas with my previous approach with all of those opcodes and things, although the compiler, if the optimizer really tried hard, it could sometimes constant propagate and work out that I was actually reading a particular variable register, it would often not. Okay, so how do we select which of these classes is right for a particular opcode? Right, I promised some C++y type things, right? Some new C++y things, new to me, probably not new to most of you. What I'm going to do is I'm going to have a templated variable, which is something I didn't know you could do. You can template on a variable, and I'm going to specialize it by instruction category. And that means I can actually have a variable that is different, has a different type depending on the parameters that are passed into its template, which blew my mind. What do I mean? Well, let me talk about this. Right. First of all, we're going to have a base case. This is a missing instruction which says I haven't covered one of the cases, and I absolutely have to have all the instructions covered, otherwise it's going to blow up. And I've used a new feature where I said you can't construct one of these things, and if you do try and construct it, the constructor is deleted, but print out this cool message, which I learned, again, from a recent C++ Weekly, which it said that you could do this. This is apparently new. Then here is our base case. For all opcodes, this variable called instruction is an instance of the missing instruction. So if you try to instantiate this right now, you'd get a compile time error saying, hey, I don't know what to do. It's a missing instruction. And now I can phrase and specialize each of the individual instruction types using requires, which is a cool feature I've discovered. Again, no surprise to most of you in this room, but it was relatively new to me, that we can say, hey, if X is 0 and Y is 0 and Z is 0 of this opcode, which is, this is just a non-template type parameter, this opcode thing that has the X, the Y, and the Z, then if you try and instantiate an instruction with that, you get a NOP. Fabulous. Similarly, if you've got X equals 0, Z equals 1, Q equals 0, that's one of those 16-bit loads. It is a 16-bit load, which is itself templatized on the P value. And this this format is exactly that list of instructions I have on that website that said this is how to decode the instructions. I can literally paste the text from the website and put it in the requires clause and say, hey, this is how you decode this kind of instruction. So that was awesome. So now we're going to work out how to dispatch based on a dynamic value to this compile time construction. So what I really want to do, again, is have this table and dispatch to it. How do I write this table? And again, this is where my brain was blown because this is how we do it, apparently. And this is, again, this sort of raises my kind of, oh my gosh, I'm just an assembly programmer hackles because this looks very complicated. But we're going to make a parameter pack and we're going to expand it. And parameter pack expansion has magical properties that lets me do some clever things. And let me show you what I mean. So first of all, how do we make a parameter pack of all of the numbers between 0 and 255 inclusive? Well, obviously, we call std_make_index sequence, right? That returns a bespoke type, which is essentially a tuple of 0 and then 1 and then 2 and then 3 and then 4 and 5. So when you get compiler error messages for this, incidentally, it's quite a long name. It's just got all the numbers from the. So thankfully, there's only 256. I'm ignoring those extended instructions for this just for the purposes of making it simpler. And then we pass an instance of this class immediately to an immediately invoked function lambda. A lambda. And we don't care about the value of it because it's not the value that's important. It's what's in that template list, which we can unpack into a parameter pack, or pack, rather, into a parameter pack. So this has the side effect of turning num into a parameter pack of 0, 1, 2, 3, and so on. Then we create an array of lambdas. Each lambda is an instantiation of this code with a different opcode number. Hooray, finally we found a way to do this. I would really wanted to use that nice constexpr, just write regular imperative code like, normal people would write. But no, you can't do metaprogramming in that way, and so I just have to accept it. Fine. This is what this is about, though, right? I'm an old dog, I've got to learn some tricks. Here's one. And then, you just make a std array of those, and we're done. So it wasn't quite as bad as I thought it was going to be. It's sort of relatively isolated to this area. And then coming soon, those of you who are on even newer pieces of code, this didn't work on Clang 20, which is what I was using, you can actually do this syntax to unpack an index sequence directly into a num, although there's some interesting caveats with that. So, does it work? Well, yes, of course it does. Yes, hooray. This one, anyone? What was it? Oh, no. Daley Thompson's decathlon this was, which coincidentally, a few weeks ago, I was in a friend's museum, and I live in America now, so he's got a computer museum in America, and I found a copy of Daley Thompson's decathlon in a drawer somewhere, and I don't know how he's managed to get hold of it. Okay, it works, hooray. Let's look at the code generation, which is really what I'm here for, right? This is beautiful. I know you don't appreciate it, perhaps in the same way that I do, but this is how to dispatch one instruction. It's exactly what you'd want. In fact, it's so small, I was able to annotate every single line of it. I'm not going to go through it here, but it just does the minimum amount of work needed to work out which thing to dispatch to and then jumps to it at the end. Fabulous. Let's look at one of those opcodes to see that there's nothing extraneous going on inside of it here. So this is exchange AF with AF prime, so it's just switching two registers, and it just reads the two and writes the two out again. No further indirections, no table lookups, no nothing. This is gorgeous. How long's the symbol? Oh, yeah, sorry, I actually deliberately, thank you. Jason asked how long the symbol name was, and it's a reason why I deliberately left overflow on. Yeah, this is one of those things. Oh, hang on, if I can get my mouse to do the thing. Oh, I'm scrolling on the wrong window because I'm looking at my notes. Somewhere in here is a mouse pointer that can come over. There we are. Okay. I'm a professional. Yeah. Now, I'm going to point something out here. This is cool, right? So embedded in that is like a mnemonic, one of those classes that is a compile time class that just holds strings. And as of Clang 20, but not Clang 19, it kind of makes the guess that if you have an array, a std array of chars, it should print them out as that, which was super cool because otherwise it was 16 numbers, one after another, which obviously was not very helpful, or 10. Anyway, thank you for the distraction. Now, that's cool. It keeps going. Yeah. And there's the lambda. Hey, right, okay. So that's exchange AF with AF. 16-bit adds are a bit more complicated. But, like this is, we look it up in the table. Here's a little bit of code. It devolves to this. Just read the two registers, add them together, write them back out again. account for 7 cycles. I haven't really talked about time passing, but that's an important thing to measure as well. That's cool. I'm going to ignore the flag handling code because you saw how hideous the C++ code is. Nothing to see here, but it is there. But that was the same in the old implementation, and I have some ideas about improving it. So let's get on to build times, because this is the thing that's close to my heart. If I touch the CPP file, or one of the CPP files in this half of the project, it takes me 3 or 4 seconds. I'm happy enough with that. But realistically speaking, all of the actual guts of the code is in a header file now, because it needs to be included in a couple of places, one for the disassembler, one for the actual running part of the code, and for the tests. And now suddenly my build has jumped up to a very variable 11 to sort of 20 seconds. And it really depended on what else was going on my computer, because each of the compiles was really big and weighty and required all those massive instantiations of templates, and so took up a lot of RAM. So I noticed some swapping. Again, this is all measured on my computer, so it's not particularly representative, but it's representative of my flow. So not ideal, but also not really as bad as I thought it was going to be. And I'm sure there are tricks to make it go down. So maybe I should just not keep banging on about build times. I don't know. Performance, 200 times faster than the Spectrum, twice as fast as the last one. It's fabulous. 650 megahertz computer, that's pretty good actually. Given that this is only a like 1.5 megahertz, 1.5 gigahertz machine. That's not a bad clip. And in fact, I can get it up to about 1 gigahertz if I slightly cheat. Cool. Well, okay. So we've got an experimental version 2 that we can play with. And the first thing I wanted to do is say, can I use modules? Because I've heard they're a bit flaky, but they might be the solution to all my build woes and my build time woes, right? There's some laughs in here for the recording. Yeah. And also, anyone know what this game is? It's not Nightlore, but it is similar to Nightlore. Go on. Head Over Heels? No, again, it's a similar engine. It's Sweevo's World. Oh, okay. I have found something so obscure no one else knows what it is. That's fantastic. All right. Coincidentally, I was asking Claude for suggestions for which Spectrum game best represented each section, and it picked this one. Because of the sort of modular look, I suppose, of the isometric game. All right. So my hopes here, cleaner separation, because that's what modules are really about, right, is to get rid of the sort of the preprocessor and all the hell that comes with it. And then obviously my secret hope is a faster build. As John Lakos is in the front row here, and he knows, in the early aughts, I started a business on the basis of his book, large-scale C++ design, because it brings down build times generally, and that was fantastic. And ever since then, I want my build times to be low as possible, and I'm hoping modules will do this for me, but we'll see. Okay. So this is what a module looks like. So we start with a big line that says module. And the cool thing about this is that you can't put any preprocessor nonsense before the word module or it doesn't work. So unfortunately, I can't conditionally make something a module or not. So I have to either be fully module or not module or do something else. And I chose to do something else, which I regret, but we'll come back to that. There's a lot of regret in this talk. Okay, we sort of say what we're exporting, and you can export a module, and you can also export a partition of a module. And for what it's worth, I am not trying to represent myself as an expert at this at all. This is me trying to get it to work and then randomly posting on Blue Sky and getting people to help me until it worked. Importing is so much nicer. I can just import all of std. No more remembering whether it's algorithm or is it numeric or is it, whatever, ranges. You can also import local partitions within your own module and say, hey, there's another part of my little localized area that is supporting the mnemonic stuff. I'm going to import that here as well. It's sort of the equivalent of like including a local header. And then you just put the magic keyword export in front of things that you want to be visible to the outside world. Fabulous. And then the rest of the code, you can kind of write it like it's Java. I hate to say that at this conference, but no, I don't think anyone's done a talk on Java, but anyway. It's just you write it out in the header. And I suppose, again, to sort of explain myself here, most of you all will probably write stuff in headers because, you like header-only library type things. I abhor them, unfortunately, and I try and hide my terrible, awful code into the CPP file so that no one can see it, not even the compiler. But this was kind of nice because I didn't have to keep making the decision. Is this something that should go in the header or is it something that should go in the CPP? It's just all in there in a big blob. Brilliant. Build support was surprisingly good. I have a contemporary CMake and I had, Clang 19 and then I moved to Clang 20 during the middle of this project. You just say, hey, this set of files is CXX modules. And then I chose to call them all CPPM files for C++ modules. That seems to work. the files are there, and I've got this module.cppm, which is where I kind of import the local parts and then re-export the whole module as a whole to the outside world, but with only the bits that I want the outside world to see. Outside world for this component, that is. Right. Hooray. And now, unfortunately, the bright and hopeful voice goes away, and we start talking about what actually happened rather than what should have happened. Import stood didn't work. It was lovely. There was this ridiculous SHA-256 value I had to set to some mystical value inside CMake to make import stood work. And it did, in its defense, it did work as much as I could do import stood. But if I tried to use any other library that itself pulled in standard headers, I would get not the clashes you would expect of like, hey, stren is defined in 2 places, but some unusual ABI tags would get noted as being different. Like it said, you know, underscore v2 underscore ABI tag is duplicate defined. I'm thinking ODR, panic, oh my gosh, this is going to go horribly wrong. And I asked around, and the received wisdom was, oh yeah, they need to fix that. And I'm like, ah. I also noticed that because I have link time optimization turned on for my release builds, because I do tend to hide all of my code away from the compiler and my CPP files, but I do like inliners, so I'm kind of torn. There was a weird thing where the import stood and LTO just fought each other. And so every time I was building a release build, it would just rebuild everything from scratch every time. I'm like, no, don't do that. Don't do that. So I couldn't get it to work, and I eventually turned it off. And then I was kind of telling a fib earlier. This format over here is not actually what I went with. What I did is I had line 12 be hash include the CPP file. And then I could keep both the CPP file and the CPPM file and have a dual build. But then there was all sorts of other horrible hash if-defs I had to do to stop me from including, and it wasn't the best choice. So in fact, after I wrote all these slides, I went away and made a branch, and I did modules kind of, quote, properly, and I still had problems. And all of the things you're about to see in the next slide, this, happened in that branch. So although if you go to look at the project now, it's on GitHub, it has that horrible hash include hack. This is what I saw when I did it, quote, properly. And that is the surprise to me, right? If you have 2 components that share a header file inside your own project, then if you make a change to that header file, the 2 files that include it will build in parallel, right? They can both include the header file, they can both go off and do their work. It means they're probably doing the same work twice because they both have to parse that header file and do some work with it, right? That's a pain, but at least I can parallelize it. If you're using modules, and again, hopefully someone can correct me on this, but if you're using modules, I can't even import the other module until it has been built, which means that it runs and it compiles, and then and only then can I import from it and see which symbols it actually has in it and then use them in my compile. And so what I found was, if I dump out the build graph, as in like what happens if I touch this file, there was, in the non-module case, it was like clusters of like these 4 files built together, then we link them, and then these 4 files built together separate somewhere else, and then we link them, and then they use each other's headers, and then those get linked together, you know, like the usual pattern you're expecting. The header files are like the sort of like the layer of separation. What it meant is essentially everything was linear. It's like, oh, this project needs all these things, and all of them need to build individually first before they can include each other, and then they get linked together. And now, finally, we can start using things that include the headers. Does that make sense? Sorry, I realized I went a bit gabbly there. But it serializes the build, and maybe I'm doing it wrong. And build times went up to 30 seconds. That was not what I was promised. You know, for reference, remember it was 10 seconds before, and now it's like 40 seconds. That's no good. And a clean build, which I didn't show on the other things, is like 2 minutes versus 1 minute. It was a disappointment. So overall, I love the modularity. I got so many flyby includes discovered. So I was using, you know, size T instead of stood size T in a bunch of places. I was using all sorts of other headers. It was lovely for just getting that sense of I'm definitely importing the right things and I'm using them from the right namespaces. Lovely, love it, brilliant. Probably more experience is needed to be able to do this properly, and certainly the linearized build, maybe I'm just doing it wrong, it's quite likely. Tooling would help. A lot of the tools didn't work all that well with modules. Clang Tidy, for example, seems to not like it. We need some best practices. Luckily, I think there are people in this room who might be able to write some once things have settled down. But I do think it's close, right? The fact that I was expecting seg-faulting compilers or it just not working at all, I got it to work pretty quickly, and it mostly did what it was said. It just needs to be better. And I think that's a great place. So let's talk about coroutines. I wish to heck that I had been to this conference before I prepared this talk rather than afterwards, because there were 3 separate talks on coroutines 2 days ago, and I would have done a much better job of it if I'd have been to those talks first. So take this with a pinch of salt and either speak to Phil or one of the other presenters about coroutines, because I think I'm doing it wrong. In fact, I know I'm doing it wrong now, but you can learn something from my mistakes. That's kind of why you're here, right? That's head over heels, by the way. Yes, it says it, sorry, in big letters. So, why would I want to use coroutines in an emulator? What on earth is the point of that, right? Coroutines are for like concurrency or I/O or threading something. Well, first of all, they're not just for threading. They're for things that are running at the same time. And if you're emulating something accurately, you're not just emulating the Z80. I know I showed a picture earlier where I said I run the Z80 for a 50th of a second and then I put the picture on the screen. That isn't how it works, really. Because video game developers, I'm going to stare at the video game developer again, like to play tricks like, hey, if I change this color while the picture's being physically painted, I can make it look like there are more colors available than there are on the real computer. Oh, so if I emulate them separately, I won't see these effects that you get when game programmers use cool tricks. So you actually want to do something like this, where here when I'm reading memory, it takes 3 cycles, cycle pass time. When I did that add, the 16-bit op, it takes 7 cycles to do an add. And then what does Z80 pass time look like? It looks like this. Hey, just account for 7 cycles and then tell all of the bits of hardware, do whatever you do in 7 cycles, please. So the ULA, the video chip, the audio chip, the tape system when you're emulating a tape, do some work, do 7 cycles worth of work. That's easy if all you are is a counter. You just bump your number up by that. But if you're a sort of stateful system, I don't know, like a video chip, then what you end up writing is sort of a horrible state machine where you have to kind of manually say, well, if I'm in the bit where we're at the top border, then I need to write out some things. But if we get beyond some point, if this many cycles have passed, now I move into the next state, which is now I'm doing the left-hand border, until eventually I do the bit where the screen, and it's just a pain. It's a pain. And realistically, the Z80 should work this way too. It's just that I'm using the Z80 as the thing that primarily drives the rest of the system. You could imagine if I had 2 Z80s, if this was a multi-processing system, that which Z80 is in charge and which Z80 is told, can you just run 1 cycle? How do you run 1 cycle of a 7-cycle add? You have to write everything as a giant state machine, right? It would be really awkward. But that's what coroutines are for, right? How much nicer if I could just say my video chip, like the physical video chip, runs all the time, right? As soon as it's got power, that thing's doing what it does. And what it does is it starts at the top of the screen, and every cycle for some number of cycles, it waits for the next clock cycle, right? Raising edge of the clock cycle, and it writes out 1 pixel of the border color. Whatever the border color is currently, I'm going to write it out, and then I'm going to go around in my loop. And then for the next 192 lines, the whole 192 lines of the screen, yes, the whole screen is 256 by 192 in today, I forgot to say, which is about the same as a capital W on an iPhone screen right now. How far we've come. I was actually speaking to someone in the pub, and they were like, oh, I was doing a presentation on emulators, and I kept trying to find a high-resolution screenshot to put in my presentation. And then I realized, oh, no, they were all that size. Yeah, that is actually the right size. So, you can write it this way, and we just want to wait for the right amount of time and let the other things in the system do their thing until it's time to come back to me, and then let the compiler do all the hard work for me. And so coroutines, and again, no expert, obviously no expert. I think by now you've worked out my MO. Any routine that has the co-statement, any of the co-statements, co-await, co-yield, co-return, gets magically transformed through a very arcane and complicated but very powerful process. We're not going to go into all these details. Go watch one of the talks from this very conference on it. But I like to think of it as it's a bit like a lambda. You know how when you make a lambda, you know that behind the scenes some structure is being made with a call operator, and any of the captures get copied into that lambda and held as variables, and then you just call the call operator and magic happens there, right? This is like that on steroids, where what happens is for each time a co_magical operation happens, that the code between that and either the top of the function or the previous co-routine is kind of broken into its own sub-function, and then we hold in the state, in sort of the lambda state, we have all of the local variables that are shared between everything, and then we have like a pointer to which function is the function we would resume at if we were to come back to this coroutine. And we start off with some initial state, although that can be configured. Everything can be configured. That's what makes them awesome. Yes, that was a Freudian slip, shall we say. Let me get mine. And so like the init will do like everything from the top of it and sort of set all the variables to their initial variables and then say, let's go to step 1. And then it returns some magical thing that you can control when it will get scheduled again, when it will get resumed. Step 1 looks like this. This is the top of that bit where the border was happening. We kind of wait that many cycles. And then when we reach the right point, we set the Y value to 0, which is now the Y at the top of the screen. And we go to step 2. I think you get the idea, right? Some magic has happened behind the scenes and it's written the state machine for us. That's what I want from it. And that works beautifully. It works great. There is a little bit of, when we first call the function, where are we? Right at the beginning here. When you call this video run and it spots the co-await, some machinery comes in and all that state that we were looking at, that state object, gets allocated somewhere. So there's a bit of an allocation somewhere. Sometimes the compiler can elide them, but in the case of the situations that I'm using here, it won't be able to because they're very, very long-lived. So that was a pain. Get out of there. The Z80 now would look something like this. You know, this is what the main loop looks like. I didn't show this before, but you know, we do an operator. Oops, hang on, haven't done the things. So what we're going to do is we're going to say like reading from memory takes some time, so I have to co-await it, and that will effectively deschedule the Z80 at this point. Let the video chip do 3 cycles of drawing pixels, and then it'll come back to me and go, "Hey, 3 cycles have passed. Read the memory now." And then I need to dispatch off to my opcode, and this is where the problem starts. Right? Because this function here, instructions table opcode, also will need to read memory and let time pass. So it kind of needs to be a coroutine as well. But I don't want to create an allocation here to do that. And it can't live on the stack because I know I'm going to be yielding to God knows how many other processes. So there's going to be an allocation here. And so what I really want to be able to do is, you know, in our execute routine, I need to be able to do this co-await again. And I couldn't work out how to do that without causing an allocation pretty much every cycle of the machine, which is, you know, 100,000, no, whatever, 100 megahertz, yeah, 100 million times a second, which doesn't sound something that's very feasible. Now, I could probably do something clever with allocators, but there's a lot of stuff going on there. And so this was a bit of a shame. And I basically gave up at this point, I'll be honest, and during this last week, in every evening, I've been trying to go back to it, having like channeled what I've learned from Phil and co, and I haven't been able to resurrect this and get it in the way that I want it to work, right? And the way it should work. And I actually cheated, and I asked on a forum somebody who had a C++ coroutine emulator of the Game Boy, and they sent me the link to their GitHub repository, and I was like, oh, how are you doing this? It looks like it's doing what I'm doing. And every function call that it was making that was, you know, like, hey, handle read, handle add, handle whatever, was a macro that was hash defined. And so effectively, it was just one big coroutine. The whole loop, every single function call wasn't a function call. It was an inline macro that then meant that like everything was living in the same coroutine. And that was kind of, oh, I don't want to take on coroutines, but have to use macros. That seems like the wrong choice there. So I'm going to have to come back to this, right? Coroutines are awesome. There is a learning curve. Maybe they're too complex. I don't know that they're too complex. They're about as complex as they need to be. Obviously, there are libraries on top of this that you could probably use. I've got a lot to learn. Okay, we're doing pretty badly on time. I'm going to have to speed up a little bit. So, future directions. Where can I go with this? So I've done coroutines. We did concepts and constexpr, and I've showed you how terrible a programmer I am and how I shouldn't be allowed to write code anymore. What would be really lovely is to be able to like take games and just play them wherever I am, right? Oops, let me go back here. Whoops. Oh, I've given the game away now, bollocks. There we go. And so I'd like to be able to play my game in my slides. I don't want to have to run a program like I was running before. I want to be able to play Jetpack in a web browser inside, because, you know, all my other emulators are in a web browser. So I thought to myself, how could I possibly achieve? Oh, Cisco, good. I love this game. This is actually probably, all right. This is actually what I was hoping to be able to do. This is my ultra stretch goal. And yes, some of them from Rare is here. So yeah, please don't get me in trouble with this one. You can take the picture, but just please don't come after me. I have got the cassette tape somewhere, I promise, for the purposes of the legal people. So yes, I wanted to get it working in the web browser, and I obviously have, which is great. And it was a lot easier than I thought it was going to be. WebAssembly isn't that hard, especially when you have a very controlled environment where effectively the entire emulator is an exercise in a 64K buffer making changes to itself over and over again, right? That's all that the CPU is doing to a buffer of numbers, right? So there's not really many things from the outside world that need to come in. I just need to be able to take the picture out occasionally and put the keyboard presses in. So you have to grab something called WASI, which is the WebAssembly system interface. It's kind of like the operating system that you're cross-compiling to, because you can't compile for a regular C++ library. No such thing exists for JavaScript, which is what we're going to be embedding in. And then you need the component in the JavaScript side that pretends to be like the operating system, and it says, hey, this big area of memory, I can malloc and free it to you by handing different amounts of this RAM to you. And if you need to be able to read and write files, then you call these functions, and it goes out into JavaScript world, and then JavaScript does whatever JavaScript do. And then the build settings are as simple as this. I just said target wasm32 WASI, and I pointed at where I got the system root for the cross-compilation to. And it just worked by and large. There are a couple of caveats which you can talk to me afterwards. There's some wiring you have to do, everything's C. So there was one of the interrupt conversations we went to earlier. We talked about this, of course, everything's C. There's some magical Clang stuff that you put in to sort of say how to export things. Everything is a number on the remote side, because all you're really doing is looking to the window of a computer's RAM, like this virtual machine that your WebAssembly runs in. So everything's virtual machines and RAM blocks. There's some magic in here on the JavaScript side. You don't need to worry about this. I wrapped it in a JavaScript class. So I think this is the only JavaScript that's been shown at this conference, maybe. Oh no, we had one. Yeah, exactly. And so all we're really doing is just doing a little bit of very light interoperability between the things where we're sort of passing the this pointer in to a function. And one of the things we can do is we can form an array over a subsection of the RAM. So I can call a function in the C code that fills in a std vector with all of the RGB values, and then I can map that in JavaScript side as a uint8 array, and then pass it to the blit function to draw it to the screen. So that's how we can draw it to the screen. And when it crashes, you get assembly in your web browser. How cool is that? I couldn't not have a slide with assembly on it from a web browser, but this is not mine. This is built into Chrome, right? So this is what you get. It's a really weird thing. It's a lot of fun. It runs at about 100 megahertz, so it's not as fast as even the NAF version. I was using the V2 version for this. It is live at spectrum.xania.org if you want to go and play around with it. And clearly, C++ is the future of web development. All right, the real future directions, the performance can be made better. That is what I love doing. That's really my happy place, is making things go faster. There are some really neat tricks involving computed gotos in regular emulators to do with how the branch predictor fits into all this, which I definitely don't have time to go into. I'd love to support more of the Spectrum family. And moreover, I'd really want to get coroutines working. I think there has to be a way, and it seems so natural, and certainly it would allow me to add more peripherals more easily without writing horrible state machines myself. Super stretch goal would be to get just-in-time compilation, turning the Z80 into Intel x86 and then just remembering the Intel 86 and like just calling it over and over again. Turns out to be spectacularly hard because back in the 8-bit days, almost everyone used self-modifying code, so the code would change all the time. I know I did. All right, these are the extra bonus slides that I had to put in because Daisy. So Daisy nerd-sniped me into thinking, when she was showing how the Claude command line tool was able to like make changes to the Clang code base. So I thought, well, AI's not coming for my job. So I said this to Claude. This is a shortened version. This is a part of a presentation I'm doing on modern C++. I'd love to demonstrate something cool you could do in my code base. A suggestion would be to add tests. What would you suggest? I thought I would give it a really low-ball idea about adding some tests to a project. That was one of the things that she said was kind of it would be good at. So it went off and it ruminated on my code base and it asked some questions and I went back and forth. And then it came back with this. And I said, think harder, right? We learned that was the hack. Magic hack. This is what Claude came with. Based on my analysis, real-time ray tracing. AI, it's no tests. I'm not writing tests. Even the AI doesn't want to write tests. C++ 26 reflection-based game state debugger, that would be cool. But my top recommendation would be interactive spectrum memory heat map visualizer. This is a pre-seed version. It was a lot more involved than that. It was so much fun, right? So I said, all right, go on then. And it bloody did. It just did. And I'm going to very quickly try and show you what it did here. So I have to do, it put it behind a command line flag, so it's not on all the time. But effectively what it's doing, and also it wrote me a readme, and I keep putting the mouse pointer the wrong way. Let's go over here. So there's an overlay over the screen now, and the hotness, as in how often a particular memory location is being either read or written to, is superimposed over. So the whole 64K is kind of superimposed. So you can see the red areas are where it currently is reading and writing to, and it even put in some keys so I can control it, and it gave me 3 different color schemes, which is cycling through my, so there's spectrum, there's grayscale, and then there's heat, which aren't showing particularly well here, and I'm just making a pig's ear of demoing it, but you can definitely see something's going on here. These red marks are like wherever, maybe some important variables that the thing is using all the time. I don't know. It's a way of kind of getting a sense about what's going on. I've got it to compile last night, and I thought, oh, sugar, now I need to write some slides about this, and I don't really know what it's doing. But that might actually be a cool thing to add. But like, it did it all itself. And so I am mildly worried for my job, but not that much. Who's going to stand up in front of you all and tell you about it, eh? All right, there we go, click. So in conclusion, as I am very much over, is there hope for me as an old dog? I like to think so. I like to think so. So what are my takeaways? What am I going to say to you? What am I going to exhort you to do as you leave this room and go home? Well, the main thing that I learned as a sort of 30-ish year veteran of doing this is I felt frustrated. I felt annoyed. I thought it was stupid. I thought the standards committee have got no idea what they're doing. Everything's too difficult. And then I remembered, learning is uncomfortable. That's what learning is, right? You forget. If you're a senior person like myself, who's been doing this a long time, kind of a lot of things come easily, and you kind of get used to that. You get in the groove of like, yeah, I'm just going to knock out a class, I'm going to do a test, everything's easy. And then something turns out really hard, and you think this is dumb. And you go, no, learn how to do it. Spend some time with it. Get frustrated. Come back to it a week later and go, hey, that wasn't half as bad as I thought, That's definitely what I've learned from this, and it's been so valuable. It's the reset I needed. Challenge your assumptions. Maybe 10 seconds of build time is perfectly reasonable, Matt. Maybe. Hopefully you realize that I love this, right? Do things that bring you joy. I mean, I'm so lucky to have a time like this to be able to do this kind of thing. And I'm so lucky that I can write a program that is fun for me at every level, even when it was frustrating, even when it took me 6 weeks instead of the 3 days I originally thought, because software engineers just can't estimate time. And then, even though Claude won't do it for you, testing is worth it, right? One thing I didn't say is the V2 version that I did worked first time once all the tests passed. As in, like, I had my suite of tests, it would tell me, oh no, the ALU is broken, all right, fix that. Okay, now, okay, the add isn't working right, okay, that's the add. Okay, now this instruction is working, okay. Oh, all the tests passed, cool, all right, throw manic miner in it. Oh, and off we went. It was just a joy. So write tests, they're good. We know that, right? But it's kind of nice to be reminded of that. So let's quickly revisit my preconceptions in the no time I have left. Build times, they did get worse. Does it matter? Probably not. No, maybe in bigger projects we need to think about this, and I'm hoping that the people in this room will sort out the modules problems and will continue to give good advice about how to properly segment parts of your code base so that the build times in one area don't necessarily impact the other parts. Bad error messages, no, they're all great. Compilers have gotten so much better. This looks bad, but it's telling me exactly which constraint wasn't working, and it's pointing at the exact thing that isn't fitting that. And like we saw in the earlier part, even the stupid symbol names where I'm using like packing names into types, it's now showing the name inside the type. So that was great. Oh, I'm showing it there, right. Modules and coroutines, what do I think about them? Modules, 2025 might be the year of the module. It might be. Coroutines are ready. Go and use them. If they make sense for you, go and use them. There are plenty of good libraries out there that I haven't shown. But they make coroutines tractable. Things like just a generator, if you can use it, that just works, it's great. Are they too complicated, maybe? Or maybe that's just this old dog going back to his old ways. Tooling wasn't that great. This is the otherwise excellent C-line getting very confused about all the things that I was doing when I kept switching backwards and forwards between the module view and the not module view. So I didn't like the tooling support wasn't great. ClangD would keep telling me that things were uninitialized on the line that was initializing them. And I'm like, no, it's there. Build times, obviously, I'm going to complain about them forever. There was just a woeful lack of any kind of context for compile time string manipulation. You have to kind of roll your own, and that's kind of annoying, but it was not the end of the world. At one stage, I resorted to turning the register, a constant offset into an ASCII value by adding it to single quote 0, which is, like, I just want to use std format here, please. So std format would be nice. I did like the performance, and actually that version 2 thing was great. Phrasing it in that elegant way where the requires clause matches exactly what the spec said was just beautiful, and knowing that it all just worked. The Java-like modules were good, and of course, I loved learning new things. So we get to the thanks slide. Huge thanks to Hana Dusakova, who was really the co-author of all of the intelligent parts of this presentation. Thanks to everyone else. I hope you like your suitably awful spectrum renditions of your photographs and whatnot. In particular, the Compiler Explorer. If you've noticed how rubbish it's been for the last 6 weeks, it's because I've been doing this and not actually... I can feel my phone vibrating in my pocket as I'm being texted about more things that are wrong with it, but never mind. So, as the end of this presentation, go and build something cool and learn something from it. Thank you very much indeed.